Good afternoon, class. Chapter 2, limits. Here's 2.5, continuity. So we covered limits of sequences, limits of functions at infinity, limits of functions at finite numbers, algebraic methods, and now continuity. Recall, when we look at this expression, the limit of f of x as x approaches a equals L. That's what it reads. When we discuss sequences, the limit of a sub n as n approaches infinity equals L, we say that a sub n converges to L. Limit of a sub n as n approaches infinity is infinity, negative infinity, or does not exist. The sequence diverges. And to find limit, simply plug in and observe. If we look at all of these cases, as x approaches a from the left and right, then we can see the limit exists, and the limit of f of x as x approaches a equals L. What's the difference? In this case, f of a equals L, the functional value equals L, and that means it's really continuous at that point. In this case, f of a is something else, b, not equal to the limit, makes it discontinuous. And in this case, the functional value is not even defined, but in each case, regardless of what happens to at a, limit of f of x as x approaches a equals L. Horizontal asymptote, the line y equals L represents a horizontal asymptote if the limit of f of x as x approaches negative or positive infinity is L. The line x equals a represents a VA, vertical asymptote, if the limit of f of x as x approaches a, or a from the left or right, is negative or positive infinity. And finally, the limit exists if one-sided limits are identical. In other words, the limit of f of x as x approaches a from the left and right are the same. Now, continuity. A function f is continuous at x equals a if limit of f of x as x approaches a equals f of a. Meaning, number one, f of a exists. The output at a exists. That means f of a. Number two, limit of f of x as x approaches a exists, and it's equal to L. And finally, the two are identical, meaning the limit of f of x as x approaches a equals f of a. That's what this means. The limit is the same as the output. A function is continuous over an interval I if it is continuous at each point a in I. If f is not continuous at x equals a, we say that f is discontinuous or has discontinuity at x equals a. Direct substitution property, a continuous function at a has the following limit value. Limit of f of x as x approaches a equals f of a. Functions with the direct substitution property are called continuous at a. So let's take a look at this graph and discuss at which numbers or points is f of x discontinuous. So, and then what? So we start from on the x-axis from the left to right. The very first number is 1. The second one is 3. And the last one is 5. So it is discontinuous at 1, 3, and 5. So why is that? Let's look at each case, starting with number 1. Take a look. F of 1, I don't say solid point, f of 1 is not defined. However, as far as the limit is concerned, as we approach 1 from the left and right, from the left we are here, from the right we are here. In both cases, we are moving towards this point, which has a y coordinate 1. So the limit exists, and it's equal to the limit of f of x as x approaches 1 equals 1. What about number 3? At number 3, we notice the limit of f of x as x approaches 3 does not exist. Why is that? So take a look. We're going to look at one-sided limits. Limit of f of x as x approaches 3 from the left. So from the left, we are moving this way, and we get to this point in a limit sense, and it has a y coordinate negative 1, my apologies. And as we approach it from the right, we get here, we're moving in this branch, We are moving towards this hole, which has a y coordinate 2, and the two are not the same. The limit doesn't exist. So the function is discontinuous. Just in case, what is the functional value? At 3, you look for a solid point. This is a solid point having y coordinate is -1. By the way, because the limit from the left and the functional value is the same, we say the function is continuous at 3 from the left. Nevertheless, it is discontinuous at 3. The last one is number 5. So let's look at what's happening with number 5, and we notice the limit of f of x as x approaches 5 is not equal to f of 5. Why is that? Take a look. As we approach 5 from the left and right, we are here. Left is here, right is here. Both of them take us to this hole, which has a y coordinate 1. So the limit exists and it's equal to 1. However, the functional value, we look for a solid point, is the y coordinate of the solid point, which is 3, and they are not equal. So nevertheless, it makes it discontinuous. So we discussed why the function is not continuous at those points. The function g of x is a piecewise defined function equals 1/2 x plus 3 for x less than -2, and x minus 1 for x larger than or equal to -2. Is g of x continuous at x equals -2, why or why not? Well, this is a piecewise defined function, as I mentioned. And each piece is a linear function. So if you look at the top one for the sake of argument, so let me write it here, and I'm going to call it y sub 1. It's 1/2 of x plus 3. And if we look at the bottom piece, let's call it y sub 2 equals x minus 1. Each one is a line, and each one is continuous from negative to positive infinity. Therefore, this is continuous from negative infinity to -2. This is continuous from -2 to infinity. And therefore, we're going to look at the end point, namely -2. And because continuity means limit equals to functional value, we look at three things. One of them is the functional value. The functional value takes the equality. And g of -2, this is one way to write it in math. X minus 1 such that x equals -2, you plug in, you get -3. And we're going to look at the limit from the left and right. So left side limits. The limit of g of x, let me erase my work. The limit of g of x as x approaches -2 from the left, it uses less than this piece, and 1/2 of x plus 3 as x approaches -2. If you replace it, -2 and 2, they cancel each other. They give us -1 plus 3 equals 2. The right side limit, larger than, uses this piece. The limit of g of x as x approaches -2 from the right uses the bottom piece. X minus 1 evaluate at x minus 2 as the very first piece is -3. Obviously, the left and right side limits are different, so the limit doesn't exist. So limit of g of x as x approaches -2 from the left is not equal to the limit of g of x as x approaches -2 from the right. Therefore, limit of g of x as x approaches -2 does not exist, and therefore g is not continuous at x equals -2. Now, what I'd like to add here, continuity from the right or left. In this case, is g of x continuous, CTS short for continuous, at x equals -2 from the right? So it could be that the function is not continuous at some point, but it could be continuous from the left and right, meaning if you look at the right side limit, okay, and the functional value, these two are identical, and the answer is yes. Nevertheless, it remains that g is not continuous at x equals -2, but we say it is continuous at -2 from the right, in case. Types of discontinuities. Well, let's look at what we have here. We have a line with a hole, we have a line with a hole and a solid point. How do we get there? I hope you remember from college algebra pre-calculus that if you have a rational function and there's a common factor between the top and the bottom, it creates a hole. So right now, if you factor the numerator, you get x minus 2 times x plus 1 over x minus 2. These two cancel each other. We get x plus 1. But original function is this. So it doesn't change the fact that the domain is all real numbers except 2. So this doesn't change. So if you plug in 2 here, you get the coordinates for the hole as 2, 3. So in this case, we have the same situation, but it's a piecewise defined function. 1 at x equals 2, that is referring to this pair, 2, 1. And I hope you see that the function g of x equals x plus 1 is a line that doesn't have a hole. If it didn't have a hole, it would be this line, and this would be the function. And it's continuous from negative to positive infinity. So in this case, this is the same line with just a hole because of this situation. And in this case, we have also defined that one. So I want you to distinguish among those. Now, parts A and C, these two parts are called removable discontinuities. All we have to do, we could remove the discontinuity by redefining f of x at just a single point, number 2, x equals 2. And how do you redefine it? You redefine it to be 3. So instead of 1 here, if we had 3, if we would put 3, it makes it a continuous function. So known as removable discontinuities. On the other hand, if you look at this one, you have a vertical asymptote or infinite. There's no way to fix that. In this case, we have jumps. There's no way to fix that. And therefore, we have infinite discontinuity here. We have jump here, none of which can be fixed, but removable. That means we can fix it. There is a way to fix it. All right, here's h of x. Is h of x continuous at x equals 3? And it's a piecewise defined function, h of x, x squared minus 9 over x minus 3 for x not equal to 3. At x equals 3 is 7. And I hope you see that, again, this simply means the pair 3, 7. So if you want to take a limit, because x not equal to 3, for the left and right, you use the same thing. And I hope you realize if you plug in, you get 0 over 0. So if you replace the x with 3, you get 0 over 0. The technique is factoring. And this is x squared minus 3 squared, which makes it x minus 3x plus 3. And so the limit of x plus 3 as x approaches 3 is 6. And obviously, these two are not the same because h of 3 is given as 7. And the limit exists, but it's not equal to that, because the limit of h of x as x approaches 3 is 6, and h of 3 is 7. H of x is discontinuous at x equals 3. Needless to say, it is a removable discontinuity because the limit exists. All you have to do, redefine this as, instead of 7, 6, and it fixes the problem, okay? All right, so we just plug in. This becomes 0, this is 3, this is 36 minus 42 plus 12, 3 over 6 or 1/2. Just plug in. If we plug in 3, we get 0 over 0. This is a complex fraction. The technique is LCD. You're going to multiply by 3x over 3x. Bear in mind this is equal to 1. As far as the denominator is concerned, you write it as a product because x minus 3 creates a 0, and that's a problem. As far as the numerator you distribute, you get x minus 3. 1 over 3x. Take a limit as x approaches 3. Replace the x with 3. You get 1 over 9 as the final answer. Now, at what point or points is the function f of x discontinuous? Name the discontinuity. If removable, how would you redefine to remove it? So first, we're going to go along the x-axis and find all the discontinuities from left to right. Okay, so as we move, the very first one is at -2. The next one is at -0.5. The next one is at 0. The next one is at 1. The next one is at 3. The next one is at 5. And we're going to discuss each one and what they represents. First, the easy ones, as you can see, 0 jumps from here to here. 1 jumps from here to here. And that means 0 and 1 are simply called jump. Number 3 is easy. You can see a vertical asymptote, infinite or VA, vertical asymptote, which makes the rest of them removable discontinuity. Okay, -2, -0.5, and 5. So how do we fix it? We start with redefining it. So how do we redefine it? Well, we start with -2 to see what's going on. If we look at -2, as we approach it from the left, we are in this branch. From the right, we are in this branch. We are moving towards this hole and has the limit equal to 2. So we are going to write the limit of f of x as x approaches -2 is 2. So all we have to do, because the limit exists, then redefine the functional value f of -2 as 2. That fixes the first one. The next one is -0.5. So what's happening with -0.5, the functional value for -0.5 is given as 1, but the limit, let's at -0.5, if we approach it from the left, takes us this way, from the right takes us that way, and both of them are moving toward this hole. This hole seems to have a y-coordinate 3.5. The limit exists, and it's equal to 3.5. So we write limit of f of x as x approaches -0.5 is 3.5. And if we, and again, f of -0.5 is something else, is 1. So we redefine f of -0.5 to be equal its limit. That fixes the problem. The last one is 5. F of 5, first of all, is not given. So we look at the limit. From the left, we move this way. From the right, we move that way. And that means the limit of f of x exists, and it's equal to the y-coordinate of this point, which is 5. Therefore, we define f of 5 to be 5, and it's all fixed up.